Lesson 3, Unreasonable Time. The conclusion of this, you will be able to explain the difference between problems that run in a reasonable amount of time and those that do not. You should be able to explain how both formal mathematical reasoning and informal measurement can be used to determine an algorithm's efficiency. There is a thing called big O, order of operation, or order of magnitude, sorry, that we don't look at this level of computer science anymore. You would look at it if you studied computer science in college, but it does look at the efficiency of algorithms. So we're going to look at it again from your 5,000-foot view. So first off, what does it mean to say one algorithm is more efficient than another? What do you think that means? Does it mean that it can be written in fewer lines of code? Do you mean the algorithm is easier to understand? Do you mean that it runs faster? Okay, one algorithm requires fewer steps to complete than another. The line for one algorithm curves below the other. More efficient algorithms are much more helpful as input size grows. The amount of work grows more slowly. Usually, when we talk about algorithmic efficiency, we talk about its ability to run faster, take less time. Sometimes the complexity can factor in a little bit too if it's something that may need to be modified. Now, last lesson, we started looking at how computer scientists might compare two algorithms that solve the same problem. In this lesson today, we're going to look at two different problems. They may seem similar, but as we will find out, they are actually much harder to solve than either of the two that we saw yesterday. The question will be, how much harder? Well, let's get to it. So, with our activity, we're still running a raffle. The winners, however, are not a single raffle ticket holder. It's any two tickets that add to the winning number. And oh, the winning number is 1,000. So, everyone do this. You generate a ticket. Silently, if we were in class, you would move around the room to see if you're part of a winning pair, meaning two tickets that will add up to 1,000. Since you're doing this all by yourself, maybe generate 10 tickets and do a quick find. Can you generate a winning pair? Pause the video and try that. How did it work out? All right. Now we're going to try a group raffle. The winners are any group of from one ticket up to all of them that adds up to the winning number, and the winning number is 2,500. So now you're going to, everybody would generate a ticket in class, and you would move around the room and talk to people to see if you're part of a winning group. Not a pair, but a group. And it could be any number of tickets in a group. Now, to do this on your own, using the ticket generator, go ahead and generate maybe 15 to 20 tickets and see what you can do. Can you create a winning combination, a group that adds up to 2,500? Go ahead and try that. Which raffle felt like it was more difficult to check, and why? I think that you would have said the second one. As computer scientists, we're all getting better at thinking about problems and algorithms. We also saw last time that we can use a little mathematical reasoning to decide if one algorithm is more efficient than the other. Let's do a little more investigative work here on these two raffles to see if our intuitions are correct. We could write an algorithm that goes through every possible check for the pair raffle or the group raffle. Let's see how many checks there are. So, in class, you'd take a partner and you'd fill out two tables. There's an activity guide, and you would fill out the two tables. Okay. First, fill those tables out and then share your responses. You should go ahead and try to do at least the pair table on your own. And to get that table, you can go to either the Canvas course or code.org, Unit 6, Lesson 3, and find the Unreasonable Time activity guide. Okay. For this one, if you have two tickets you need to make one check. Can I add them together? If you have 3 tickets, you need 3 checks. You add the first and the second and the third, and the first and the third. Permutations, notice. If you have 4 tickets, there's going to be 6 checks. 5, 10, 8, 28, and so on. Just so you know, the exact formula for this relationship is n squared minus n over 2. You don't need to know that formula. But you should know that because of the n squared term, the graph curves up. It grows rather quickly. Any algorithm whose efficiency includes an n squared, an n cubed, and n to the 4th is called polynomial. It grows quickly, but it's manageable. How about this one for the group raffle? My goodness. If you have 2 tickets, you need 3 checks, right? Does the first one do it? Does the second one do it? Do both of them do it? 3 checks. You got to check each one individually, and you got to put them all together. 4 checks, 5 checks, and so on. The exact formula for this relationship is 2 to the n minus 1. Again, you don't need to know the formula, but you should know that because of the 2 to the n term, the graph curves up very quickly, grows fast, exponentially fast. Any algorithm whose efficiency includes 2 to the n, 3 to the n, 4 to the n is called exponential. There's another way to think about this. The number of checks required is the largest number you can make with that many bits. If I have 1 ticket, 1 check. 2 tickets, 3 checks. 3 tickets, 7 checks. That's the largest number that I can make with 3 bits. Okay? And so on. Now, polynomial and exponential both curve up. Why do you think only exponential is considered unreasonable? And here's some different efficiencies. This little green line, that's log. It's a sorted raffle. It's reasonable. Linear is a normal raffle. Again, that's reasonable. You just run through and check every raffle. Polynomial, that's a paired. That's reasonable. You could check it. The group raffle, exponential. It's unreasonable. You get just a couple of, goes up so fast. So here's the table. Sorted, normal, pair, and group. Notice with just 10 tickets, I could potentially have to check 1,024 different things. Notice that with just 1,000 tickets, I'm checking 1.07 times 10,301 checks. Okay? It's growing fast. At this point, there are more checks than there are atoms in the universe. Polynomial is bad, but exponential, oh my, it gets unreasonably large very quickly. So wrap up, there are some problems that we simply say are somewhat unsolvable, at least using an algorithm. Reasonable time is any algorithm with a polynomial efficiency or lower, like constant, linear, square, cube. These are all said to be run in a reasonable amount of time. We can write an algorithm, develop an algorithm, and write code that would solve the problem in what would be considered a reasonable amount of time. Unreasonable time, algorithms with exponential or factorial efficiencies, these are algorithms that just run in an unreasonable amount of time. The potential is there to essentially never complete the running of the program in a normal lifetime. It's just unreasonable. Next up, we're going to look at the limits of algorithms.